Before this engine ever leaves the ground, you need to understand four things: how a blade survives temperatures hotter than its own melting point, why engineers grow metal crystals in a single unbroken direction, what actually happens the first time this engine fires up, how ground crews spot a failing engine before the pilot does. A single commercial jet engine produces roughly 100,000 pounds of thrust. That is enough force to lift 16 fully loaded semi-trucks off the ground, from a machine that fits inside a two-car garage. The GE90, which powers the Boeing 777, once set a record of 127,900 pounds during a certification test. What you are about to see is how that machine gets built, one hand-finished part at a time. The factory floor looks nothing like a car plant. There are no conveyor belts carrying identical parts, no robotic arms stamping out shapes by the thousand. Each engine moves slowly from station to station on a wheeled cradle, spending days at each position. Workers in clean gear handle components worth more than a private jet. A single high-pressure turbine disc can cost over $250,000 before it even reaches assembly. A modern high-bypass turbofan, the kind powering most passenger jets today, contains around 25,000 individual parts. Some are as large as a car door. Some are thinner than a credit card. The bypass ratio on engines like the CFM LEAP ranges from 9:1 up to 11:1, depending on variant, meaning 9 to 11 times more air flows around the core than through it. Every single part must survive temperatures and stresses that would destroy ordinary steel within seconds. The story of an engine begins not on the factory floor but in a foundry. Raw nickel alloy arrives as ingots, dense, dull gray blocks that carry no hint of what they will become. Smelters heat them past 1,400 degrees Celsius until the metal flows like thick syrup. The specific alloy used in turbine blades, often called MAR M247 or CMSX4, is engineered to retain strength at temperatures that would soften most metals entirely. The choice of material matters enormously. Jet engine turbine blades must endure temperatures hotter than the melting point of the very alloy they are made from. Engineers achieve this through hollow internal cooling channels, barely a millimeter wide, cast directly into the blade. Some advanced blades contain over 20 separate internal passages. The cooling air that flows through them drops the effective metal temperature by as much as 300 degrees Celsius. This is not guesswork. Rolls-Royce, GE Aerospace, and Pratt & Whitney each spend billions of dollars annually just on materials research. The turbine blade in your hand is the product of roughly 70 years of metallurgical science, stretching back to early research at laboratories in the 1950s. Pratt & Whitney alone holds thousands of active patents on blade geometry and coating chemistry, and the finished blade still requires a human being to inspect every surface. Back inside the foundry, casting a turbine blade starts with wax. Technicians inject molten wax into precision molds to create an exact replica of the finished blade, hollow channels and all. This wax model gets coated in ceramic slurry, layer by layer, until a hard shell forms around it. A typical blade requires between 7 and 9 separate dipping and drying cycles, each taking several hours, before the ceramic shell is thick enough to withstand the pour. Then the wax gets melted out in a steam autoclave. What remains is a hollow ceramic mold with the exact negative shape of the blade inside it. Molten superalloy pours in to fill that space at around 1,500 degrees Celsius. As it cools, engineers control the solidification precisely using a water-cooled copper chill plate. They want the entire blade to become a single crystal of metal, growing from one seed point upward through the mold. Single crystal blades have no grain boundaries, the microscopic seams where crystals meet inside a metal. Grain boundaries are weak points under cyclic stress. Under the stress of a spinning turbine, they propagate cracks. Remove them entirely and the blade becomes far more resistant to the forces trying to tear it apart at 10,000 revolutions per minute. Once cast, each blade moves to a grinding facility. Computer-controlled machines remove surface material to within tolerances measured in micrometers, about 1/30th the width of a human hair. Then comes coating. A thermal barrier coating, often just 0.1 millimeters thick, gets sprayed on using electron beam physical vapor deposition to insulate the blade from direct flame. The coating is typically yttria-stabilized zirconia, a ceramic that handles thermal shock that would shatter ordinary glass. At this stage, the blade is complete, but it is just one of dozens in a single turbine stage. A typical high-pressure turbine stage contains between 60 and 90 individual blades arranged around a disc, and a full engine contains multiple turbine stages, each running at different temperatures and speeds. Before any of them can come together, the larger structural components, casing, shafts, and discs, have to be built separately. The engine casing, the large cylindrical structure that contains everything, starts as a titanium or steel forging. A hydraulic press squeezes a heated billet of metal under tens of thousands of tons of force. Some aerospace forging presses apply up to 50,000 tons of pressure. The grained structure of the metal aligns under that pressure, making the final part dramatically stronger than a simple casting of identical composition. Titanium is roughly 40% lighter than steel and nearly as strong at moderate temperatures. But it is also notoriously difficult to machine. It work hardens quickly and conducts heat poorly, so cutting tools wear out fast. Coolant floods the cutting zone continuously at high pressure. A single pass of a 5-axis CNC mill across a large engine casing can take 6 or more hours. The machine must not stop or restart mid-cut. Any interruption leaves a thermal mark that inspection will catch. The fan blades at the front of the engine are a different challenge entirely. Modern fan blades on wide-body jets are made from carbon fiber composite, layers of woven carbon fabric saturated with epoxy resin, built up in a mold by hand, then cured under heat and pressure in an autoclave the size of a school bus. The Rolls-Royce Trent XWB fan blade, for example, uses over 500 individual plies of carbon fiber laid at precise angles. A single composite fan blade can span nearly a meter and weigh less than 5 kilograms. It must survive a bird strike. Regulators require it. Engineers test this by firing a 4-pound gelatin projectile at over 200 meters per second from a compressed air cannon directly into a running engine. The blade must not fracture in a way that breaches the containment casing, which would send fragments into the fuselage. Fan blades are also hollow inside, a titanium skin bonded over an internal structure. The leading edge gets a solid titanium sheath bonded on with structural adhesive and precision formed to within fractions of a millimeter. This hard edge protects the composite underneath from erosion caused by dust, rain, and the occasional bird. That bond has to hold under temperatures ranging from minus 60 degrees Celsius at cruise altitude to over 150 degrees near the engine core. Now the engine begins to take shape on the assembly stand. Assembly starts with the low-pressure compressor section at the front. Rows of rotating blades and stationary vanes are stacked alternately in a drum, with each row compressing incoming air slightly more than the last. By the time air reaches the combustion chamber, it has been squeezed to roughly 40 times its original pressure, comparable to the pressure nearly 400 meters underwater. Then comes the high-pressure compressor. Smaller blades, tighter clearances, higher stakes. The gap between the blade tip and the surrounding casing is sometimes less than half a millimeter across a disc that may be 400 millimeters in diameter. Too wide and efficiency drops measurably. Too tight and thermal expansion during operation causes the blade to contact the casing. Getting this right requires custom laser measurement tools and repeated trial fitting. With the compressor complete, the combustion chamber, called the combustor, is installed. This is where fuel mixes with compressed air and burns continuously at around 2000 degrees Celsius. The combustor liner is perforated with hundreds of tiny holes arranged in deliberate patterns. Cool compressor air bleeds through them to form an insulating film along the inner walls, keeping the metal temperature around 1,000 degrees lower than the flame it contains. Here is where things get complicated. Modern engines try to burn fuel as completely as possible to reduce carbon emissions and improve fuel economy. But complete combustion at high temperature and pressure produces more nitrogen oxides, a pollutant tracked by the International Civil Aviation Organization. Engineers walk a constant line between efficiency and emissions, and that line shifts tighter every time ICAO updates its standards, which it did significantly in 2023. The turbine section attaches directly behind the combustor. These are the blades that extract energy from the hot exhaust gas to drive both the compressor and the large front fan. The first turbine stage sees gas entering at temperatures. The blade material cannot physically survive without active cooling. Every blade has cooling air flowing through its internal channels continuously. On a large engine, that cooling flow can consume up to 20% of total compressor output. Balance is the quiet obsession of everyone in this building. A turbine disc spinning at 10,000 revolutions per minute develops centrifugal loads at the blade roots equivalent to roughly 18 tons per blade. If one blade weighs even a fraction of a gram more than its opposite counterpart, the resulting vibration at speed becomes severe enough to damage bearings within minutes. Each assembled disc goes to a dynamic balancing machine before final installation. At this point, the engine core is structurally assembled but not yet connected. Miles of wiring, fuel lines, oil lines, and sensor leads have to be routed along the outside of the core in a precise sequence. Certain bundles must go on before others because later ones block access. There are over 5,000 individual wire connections in a large turbofan. Each one gets crimped, sealed, labeled, and verified by a technician working from a diagram that, unfolded, covers an entire workbench. The FADEC system, the full authority, digital engine control, is the engine's brain. It is a dual, redundant, ruggedized computer that monitors thousands of sensor channels simultaneously and adjusts fuel flow hundreds of times per second. If a sensor reads an anomaly, a vibration spike, a temperature deviation, a pressure drop, FADEC responds in milliseconds, before a human pilot could even perceive the change on an instrument display. Oil is the overlooked hero of this whole system. Jet engine oil does not just lubricate, it actively cools the bearings that support the rotating shafts. The main shaft of a high bypass engine spins inside rolling element bearings that support loads of tons while rotating at thousands of revolutions per minute. The oil film between rolling elements and races is sometimes only a few micrometers thick. Without continuous oil flow, those bearings fail within seconds at operating speed. Every fluid connection, fuel, oil, hydraulic bleed, gets pressure tested individually before the engine ever runs. A technician pressurizes each line to above its maximum operating pressure and watches for any drop in the reading over a timed period. Even a tiny seep past an O-ring seal is enough to fail the test. The line comes apart, the seal gets replaced, and the full pressure test runs again from the beginning. There is no shortcut here. Then comes the day the engine leaves the assembly hall for the test cell. The test cell is a reinforced concrete chamber built to contain the sound and force of full power operation. Walls, sometimes over a meter thick. The engine is bolted to a test stand fitted with calibrated load cells that measure thrust directly to within a fraction of a percent. The instrumentation alone, wired to a new engine for its first test run, can number over 1,000 separate sensor points. First light-off is tense. Engineers watch 50 screens at once, oil pressure rising on schedule, fuel flow climbing, exhaust gas temperature at each turbine stage, vibration signatures at every bearing location. The engine spools up slowly from a starter motor. A low hiss builds into a roar that travels through the concrete walls and into the floor. The numbers climb toward design values. Inside, combustion is happening continuously at temperatures no human can stand near unprotected. Operators push it to full takeoff thrust. At that power setting, a large turbofan inhales over a ton of air every second through an intake nearly 3 meters in diameter. The inlet generates a low-frequency pressure wave you feel in your chest before your ears register it. Outside the test cell, flashing warning lights keep all personnel clear. No one stands within 50 meters of the inlet or behind the exhaust nozzle during this run. The data from the first full-power run goes immediately to a team of performance engineers who compare every measurement against the detailed design model. Thrust level at standard day conditions, specific fuel consumption in grams per kilonewton per second, temperature rise across each compressor stage. If the engine delivers even 2% less thrust than specified or burns more fuel than the customer contract allows, it comes off the stand for detailed inspection. Endurance testing comes next. The engine runs for hundreds of hours under conditions designed to simulate a full lifetime of airline service compressed into weeks. Simulated altitude conditions in a sealed cell. Simulated cold soak starts at -40 degrees Celsius after sitting overnight. Rapid throttle slam cycles from idle to full power. Deliberate water ingestion at 45 liters per minute. Ice crystal ingestion. The engine must handle all of it without any unscheduled shutdown. Only after all tests pass does the engine receive its certification paperwork. Aviation regulators, the FAA in the United States, EASA in Europe, certify each engine type independently through a process that scrutinizes thousands of pages of test evidence. Certification from first application to final approval can take 3 to 5 years. Every change to the design after that, even a revised coating specification on a single blade type, requires documented evidence and often additional test hours. Certified engines are wrapped in protective covers, sealed against moisture, loaded into custom wooden and steel containers, and shipped to aircraft manufacturers by road or sea. At the airframe factory, they are lifted by crane and mounted under wings or onto tail structures using components called pylons. The pylon is not merely a bracket, it is an engineered fuse designed to release the engine cleanly if extreme loads occur in a crash, rather than letting it rotate up through the wing fuel tank. Once installed, the engine runs through a complete ground test on the actual aircraft before the aircraft ever moves under its own power. Every aircraft system interfacing with the engine is exercised: avionics, FADEC communications, fire detection loops, fuel shutoff valves. Thrust reverser doors cycle open and closed under load. A human test pilot reviews the full data set and signs off on the result before a certificate of conformity is issued. In service, the engine sends continuous data to the manufacturer through a system called Engine Health Monitoring. Every flight generates gigabytes of performance data transmitted via satellite link. Engineers on the ground can see a developing bearing wear signature or a subtle 3-degree shift in turbine temperature before it becomes a safety concern. This monitoring has made modern turbofans extraordinarily reliable. The in-flight shutdown rate is now around 1 event per 300,000 flight hours across the global fleet. After roughly 3,000 flight cycles, each takeoff and landing counts as one cycle. The engine comes off the wing for its first scheduled overhaul. At a maintenance, repair, and overhaul facility, it gets fully disassembled down to individual blades and bearings over several weeks. Every blade is measured optically. Worn thermal barrier coatings are stripped chemically and reapplied. Bearings, seals, and life-limited disc components are replaced on schedule. The engine leaves overhaul essentially rebuilt, certificated for another 3,000 cycles. The industry is now wrestling with its next major problem. Sustainable aviation fuel, made from waste cooking oils, agricultural residues, and municipal waste, can run in today's engines without any hardware modification and cuts life cycle carbon emissions by up to 80%. But current global production covers less than 1% of aviation's annual fuel demand. hydrogen combustion is technically achievable, but requires completely redesigned combustors and fuel storage. Battery electric propulsion works well below 500 kilometers, but cannot yet scale to long-haul routes. The engineers who built the engine you just watched being assembled are already working on its successor. Open rotor designs with exposed counter-rotating fan stages promise 15% better fuel economy than conventional turbofans at similar thrust. Ceramic matrix composite turbine blades can run at temperatures 300 degrees higher than nickel superalloys, allowing smaller cooling flows and better efficiency. The engine in revenue service today will look conservative compared to what gets certificated in 15 years. From a wax model in a foundry to 100,000 pounds of thrust at altitude, built by human hands working to tolerances finer than a strand of hair, certified by regulators over years of testing, and monitored by satellite from the moment it enters service. Every commercial flight you take is carried on an object this precise, built to survive 30 years of daily operation. As engines grow cleaner and quieter, how far do you think aviation can realistically go in cutting its environmental footprint? Tell me your take in the comments.